Next up, we got John Marsh. Did we get this presentation squared away?
I need to pull it up.
Oh, I'm sorry. Well, while she's loading, I think John is fairly well known to everyone within this community. He has 30 years experience in power generation and distribution design and construction and operation and maintenance. He was the O&M manager for AVEC, where he's responsible for 48 rural power systems throughout Alaska. And he left AVEC to join Marsh Creek in 2009 as division manager of alternate energy. So John is going to talk to us about a case study with the Steffes heater in U.S. Fish and Wildlife Service. So take it away, John.
Thank you, Carl.
You need your...
Well, I'm not sure, Kat, is it able to...
Might be faster just to use yours.
Technical difficulty.
Here you go. Okay.
It's on. I'm sure it's working. I think it's working, huh? Okay, well, it looks like we got the technical difficulty thing fixed. Thanks, Kat. Thanks, Carl. Well, we're going to switch it up just a little bit. We've been talking a lot about electric storage with our wind systems. The Fish and Wildlife Service project is a little bit different. It's going to be not the typical main grid connect. It's using individual little turbines specifically to a facility site, and we're going to be storing electric thermal. So in 2009, the Fish and Wildlife Service elected to continue to lower their total carbon footprint as mandated. So they had a bunch of stimulus money, ARA funds, to actually build the project. Subsequent to this, of course, is their need to continue to look at independent ways that weren't necessarily grid connected, but wanted to actually start offsetting fuel more specific to the individual facilities, whether it was a headquarters building, whether it was a sort of an employee facility, and these are all within the actual refuges. So again, this will be an independent grid connect hybrid with thermal electric storage. So the two locations in Alaska are in Cold Bay along the Aleutians and in King Salmon, the Eisenbeck and Betcheroff refuges. So the turbine that we used is the vertical axis turbine off to the right-hand side. It's a turbine manufactured by a company called Tangary, located in Vernon, Texas. Sort of interesting, when we talked to the Fish and Wildlife Service, they would not allow the typical horizontal axis turbine because of reported bird issues. So we couldn't use the horizontal axis turbine. They didn't want any guy wires existing. So all these sorts of issues that were consistent with bird migration or avian routes. Prior to Marsh Creek getting involved with the project, they started looking at this particular turbine for some other applications. It originally was thought to be used in a grid connect. And then we started looking at, well, what's the net effect going to be for the use of the turbine? Well, in some of these locations, they actually benefit, particularly the residential facilities, benefit from PCE. So our thinking was, well, why offset PCE and let the state benefit? So the other high cost of energy, of course, is fuel. So our decision was to go ahead and move into the wind to thermal concept. The turbine, again, being used is manufactured by Tangary. It's the Gale T5 turbine rated at 5 kW. It's a vertical axis, and in Cold Bay, in Cold Bay, they're on a 20-foot monopole tower. It's a great wind regime in Cold Bay. Class 7, smoke and wind, not quite the case in King Salmon. So the towers in King Salmon will be put on 60-foot towers. The location is this is Cold Bay. It's a small array of the 7 turbines. You see them on the left-hand side. Each one of those turbines will be feeding a separate facility. I have to kind of look up there. This is, for some reason, my sight screen here is not quite cooperating with me, so I'm going to have to sort of gaze up there on occasion. So the 7 turbine array, sort of on the left-hand side, they're about 50 feet apart. We're not so concerned with the placement because of the vertical axis design. They don't really have effects from shadowing like typical horizontal axis turbines do. So each one of these turbines then actually feeds an individual site. So starting at the very bottom of the screen, that facility is a new shop that they built a number of years ago, and it has in-floor heating. So it makes perfect sense to us to take the electric thermal and actually dump it into in-floor heating in their shop. The next building up is the headquarters building, and then a bunkhouse, and then the other 4 are the individual residential units for the Fish and Wildlife Refuge employees. This is King Salmon. So 2 turbines on the left-hand side is the facility refuge headquarters building, along with a new shop. Again, they built this last year, again benefiting from electric space heating in the floor. And then the other 2 on the right-hand side are residences belonging to the Fish and Wildlife employees, where we'll be using a turbine feeding each one individual facility. Again, the primary use is to displace the heating fuel. There is a secondary use. So the primary use, again, is to make a lot of hot water. The secondary use is to offset kilowatt-hour usage. Now, here was the other problem with this particular project. When we talked to the utilities, neither one of the utilities would buy back the excess energy. That was one. The other problem is, not only would they buy it, they didn't want the energy flowing back into the grid, period. So I had to do a little noodling on this one. So how do we prevent, how do we store all the energy in terms of thermal? How do we prevent all that energy from going back into the grid? What are the sort of the throttling valves to actually prevent that? Actually, I was getting a little ahead of myself here, I think. So the energy costs in Cold Bay, and I don't know that this is current. I'm not sure what the current PC rate is for Cold Bay and King Salmon, but you can kind of get an idea compared to what we talked about with Kokkinok yesterday. Fuel costs, and most of that cost, about 23 cents of that, I think, is the actual fuel cost for the electric. So the electric boilers that we're using is a boiler manufactured by a company called Steffes. What's unique about the particular boiler and why we liked it, they used ceramic bricks, about 2,500 pounds of bricks, and these bricks surround a core, electric core, and so they pull the heat away and actually store it in the ceramic. Now, the Steffes boiler was designed for something very different than what we're using it for. So if you think in terms of a lower 48, where the utilities make off-peak power available at a substantially reduced rate, the boiler then would come online, dispatched, would come online, take that cheap energy from midnight to 2 o'clock in the morning, store it in terms of heat, and then during the peak times, that heat would be available to dispatch into domestic hot water, even your heating system. So we decided to take the boiler and use it in a sort of a different, a little bit of different model. We're still working out some of the kinks with regard to sort of the control. We're using a phase angle control right now, but because we're not using it as a primary electric source, power quality. Again, the units, the resistive units, don't really necessarily care about this quite so much. But we're still trying to work out a couple of details on that. So that's what a Steffes boiler looks like. This is rated at 14 kW. And remember, the turbines are only rated at 5 kW. We decided to upsize the boilers a little bit so that we wouldn't reach our thermal saturation quite so soon. Well, you can't really see it right now. I think I've got another picture that may show the ceramic bricks. But anyway, so the ceramic bricks actually inboard of the external shrouding. And so this boiler then is actually operating in parallel with the existing system facilities furnace or boiler hot water system. So the two things we're doing with the hot water, we're offsetting the domestic hot water for the facility. The other thing we're doing is we're interjecting some of the extra heat into a residential furnace system. So if you look on the right-hand side, you see the 2 pipes going in and out. That's actually hooked into a little heat exchanger. And so as the furnace is running, it passes the hot air, much like a typical furnace does through a heat exchanger. We pass the air over the radiator, and that's distributed through the house, the facility. So to give you an idea on size, it's about so the Steffes boiler, that unit sits in the far left-hand corner. It's about the size of a refrigerator. The unit down on the right-hand side is a little Amatrol hot water storage tank, and that's connected in parallel with the existing the fuel-fired boiler, which is that little gray unit on the far right-hand side, top right-hand side of the screen. Oh, there's a picture of the heat exchanger. It's actually mounted inside the plenum of the furnace. That's on the charge air side or the hot air side of the furnace. So in the facilities where we don't have a furnace, hot air exchange, we actually plumb the Steffes unit in parallel with the existing facility boiler. So on the bottom right-hand side is a heat exchanger, and that's where they come into parallel. So we actually take the primary side of the Steffes boiler, run through a heat exchanger, and then so that the two liquids don't really intermix between the Steffes boiler and the existing facility boiler. Because the project's not done yet, I don't have a lot of data to share. So I'm hoping that next year when we come back, we'll actually have some real operating data. But this is essentially what it looks like. Again, because this looks a little funny, they're not broken. Actually, they're on a tilt tower. One of the constraints we had, of course, is that during the construction process, the cost of bringing in a crane, for example, well, you could probably roll that cost into your project. What do you do if you need maintenance? So the thought was, well, who's going to take care of these things? Well, we're going to be taken care of. Marsh Creek will be. And we just couldn't simply afford to bring in a crane or some form of lift to take the turbines down. So we elected to put these things on tilt towers. And so there's a hydraulic lift that we designed. It actually will tilt these towers up and down on an as-needs basis. So what you see in the very end is the alternator. The sails aren't attached yet. And I can tell you, if Larry Flowers were here from NREL, he'd probably take me out back and give me a little stern talking to. But we've had some problems with the couplings. And so right now we're working out some issues with Tangary, trying to fix that particular problem. They had a similar turbine up in North Dakota that actually, the coupling failed about 4 weeks ago and caused a catastrophic failure of the sails. So we're trying to work through some problems right now with the turbine manufacturer. Anyway, relatively short presentations. Any particular questions that anybody have at the moment? Cord.
John, if that's a 5 kW system with whatever foundation is there or so forth, what's a kind of typical turnkey cost for just the turbine portion for a 5 kW machine? I mean, I would expect it to be expensive, but...
Well, that's where it gets real scary. Sort of in general terms, this is 35 kW total of electric thermal in Cold Bay and 20 kW electric thermal in King Salmon. Total project costs about $3 million.
I used to stay in that residential facility in Cold Bay, and I was curious if part of the Fish and Wildlife mandate was to, those buildings have really big issues with construction. There's such strong crosswinds there that literally the wind and the rain is coming right through the house when it's really blowing, and that was summertime. So I would think that kind of leakage is also a big, when pulling all the heat out like that is a big issue on the load with fuel demands.
Well, I mean, one of the things that we would support first, of course, is conservation. I mean, things like, foam caulking around windows, more fuel efficient or energy efficient windows, for example, insulation in the roof, those sorts of things should really happen first. And as a result of that sort of problem you just described, I mean, their fuel costs are horrendous out there. So while this is going to offset certainly some of the fuel costs, they really need to be thinking about conservation as well.
Yeah, because literally the wind blows the water right into those buildings.
Yeah, we had a problem with one of not that facility there, but the one behind it. We had a leak where it actually was pouring rain right on top of the inverter. Carl.
Thank you, John. We're going to take questions later on. We're a little bit squeezed for time, and Hito wants to get Hito's presentation here because then we're going to have 15 or 20 minutes to have a wide-ranging discussion on this.